Once upon a time, well, to be specific, about 200 years ago, there was a great deal of smoke in the air. There was smoke in the streets, and lots of smoke indoors, too. It seemed very natural at the time. To have heat, you had to have smoke, even if it was troublesome. But as time went on, some people managed to be quite comfortable, to avoid the smoke. You could say they understood the problem, and understanding it, did something about it.
Well, at the end of the 18th century, this problem of how to prevent a fireplace from smoking was licked. Not by a lucky spurt of invention, but by the systematic application of scientific reasoning. This happened about 150 years ago. Was it an isolated case of applied science, technology, profiting by the discoveries of pure research? Or was it not rather the first beginnings of that close alliance between pure and applied science which we are witnessing in America today?
This is a caricature of Count Rumford, statesman and scientist, at ease before a smokeless fireplace of his own devising. He was born in America in 1753 and died in Europe, where he lived for much of his life, in 1814. He was one of the most famous 19th century physicists. His fame rests on his highly technical studies of the nature of heat, upon which our modern theory of heat is based. Count Rumford, however, was a very practical man, and, as this cartoon perhaps suggests, although his studies of the theoretical aspects of the nature of heat seemed to his contemporaries to have no practical value whatever, he himself was quick to apply many of his discoveries to very useful purposes. For example, while working on problems concerning the communication of heat, Rumford developed this piece of apparatus, and from his understanding of what happened here came an amazing number of designs for devices, ranging from fireplaces to drip-style coffee pots. You'll notice that it is rather like a large thermometer. It contains chips of amber suspended in a salt solution. Watch what happens when I warm the bulb between my hands. You can see that the particles of amber rise from the heat of my hands here and fall here. Rumford explained what happens this way.
The immediate cause of the motions in a liquid is evidently a change in the specific gravity of those particles of the liquid which become either hotter or colder than the rest of the mass. The more a liquid is expanded by any given temperature, the more rapid will be the ascent of the particles which first receive the heat. And as these warmed particles are immediately replaced by other colder particles, this must, of course, produce a rapid communication of heat from the hot body of the liquid. I had now an instrument which appeared to me to be well calculated for the very interesting experiments which I projected, and it will be easily imagined that I lost no time in making use of it.
Indeed, he lost very little time. Rumford's careful experimental work leading up to his discovery of convection currents led to a very practical paper with the very thorough title of Chimney Fireplaces, with proposals for improving them to save fuel, to render dwelling houses more comfortable and salubrious, and effectually to prevent chimneys from smoking. This is still the best available reference for building a fireplace and chimney. Rumford's work in the design and improvement of fireplaces is one of the outstanding examples of his pioneering in the field of applied physics. The smoky chimney and the smoking fireplace had cursed many 18th century homes. Others had tried to cure the trouble, but they had failed for lack of an understanding of the fundamental concepts of convection currents, the thermal flow of gases. Rumford had the modern concept of applied research. He first understood the fundamental physics of the problem and then applied himself to the practical details of construction. For instance, here is a fireplace, the smoking fireplace, in general use before Rumford's suggestion. This fireplace is simply a rectangular hole in the wall. Inside, the chimney was little more than a straight flue connecting the fireplace to the roof above. The smoke moved through the chimney in no clear way, but eddied about, and frequently returned to the room which the fire was supposed to heat. In a series of brilliant deductions, Rumford reasoned that the chimney smoked because there was no clearly defined paths for the rising and descending air currents. He saw an analogy between the smoke in the chimney and his apparatus to illustrate convection currents. The result was the Rumford fireplace and chimney. Rumford added a smoke shelf and a throat to the straight flue. These set up orderly convection currents which carried smoke from the fire to the roof without backing up. Hot air carrying smoke from the fire took a path similar to this. This flow sets up convection currents, and cold air from the top of the chimney falls down the back of the flue until it hits the smoke shelf to be again guided to the throat and heated. The chimney is successful because the throat and smoke shelf here carefully separate the flowing hot and cold gas streams. Count Rumford had also done a great deal of basic scientific study of the radiation, reflection, and absorption of heat. In tackling the design of the fireplace itself, he put these studies to good use. Here again is the usual 18th century fireplace, essentially a square box. Rumford's studies had led him to know that heat was reflected in the same fashion as light. He saw that the conventional design of his day could radiate heat only from way back in the fireplace. To improve performance of this fireplace, Rumford angled the sides of his new model and brought the back forward. This new fireplace was a shallower, more effective radiant source of heat. 2 years after these important suggestions, Count Rumford introduced a final detail to his new design, the damper. Here is his sketch. The damper increased the efficiency of the fireplace by diminishing the throat of the chimney and regulating the flow of air current in the flue. By the end of the 18th century, Rumford had so thoroughly understood and described the operation of chimneys and fireplaces that no essential improvement has been made since. But the Count's understanding of theories of convection and radiation prompted improvements in other devices. Stoves. At this time, you cooked over an open fire. The stoves were essentially open grates with the pots and pans on top of them, boiling, frying, and the cooks in front of them boiling too. A lot of heat was wasted. The problem was to transfer a maximum amount of heat from the fire to the food with the smallest amount of fuel. Rumford met this by enclosing the fire and by designing special kettles. In this Rumford design, you can see how the heat comes up through the top of the stove to play directly on the bottom of the kettle. This was the idea of the kitchen range. The one you see here was designed by him for a small household. Here is a larger one for an institution. Another of the Count's inventions was the roasting oven. The Rumford roasters were famous for years, and in old New England houses you still occasionally run across one. These were all improvements, but Rumford still looked for a more economical use of heat. Here is one of his solutions. A specially designed pot to fit on a specially designed stove. The pot fits tightly on the stove in this groove filled with sand. The heat from the stove rises to the bottom of the pot and reflects back to the stove again. The convecting currents and radiation theories again harnessed for practical purposes. Count Rumford's understanding of theory resulted in other inventions to aid the economical cook. Here is his design for a pressure cooker, a double boiler, and what you'd call a fireless cooker. These were all very useful, very practical devices. However, in this, Rumford's understanding of the physics of heat and his talent for practical design reached some sort of a peak. As you can probably recognize, this is a coffee pot, one of Rumford's many designs for a better coffee maker. In Rumford's day, the common method of making coffee was to boil the grounds in a pot, let them settle to the bottom, and then pour off the liquid. In fact, the way coffee is made in many camping trips today. Rumford was dissatisfied with the quality of this boiled coffee. In a long report with an impressive title, of the excellent quality of coffee and the art of making it in the highest perfection, the Count tells us how he spent 15 years studying the art of making coffee. Rumford tells us he liked coffee. He must have. But in thoroughness of his attack on the problem, there is a suggestion that other interests were involved too. For example, he designed coffee makers for all classes of society, for the common man, for the rich, and for the very poor. And he expresses the hope that coffee might replace gin as a popular beverage. However, quite apart from these interests, Rumford's preoccupation with coffee making had a direct connection with his knowledge of physics of heat. He carried out a long series of experiments which determined that the taste in coffee was contained in the volatile oils. Any coffee-making process which led to the evaporation of these coffee oils, he reasoned, would be detrimental to the taste of the finished coffee. He saw that when coffee was boiled in the traditional way, the stirring action of the boiling water caused some of these oils to be lost through evaporation at the surface of the water. He also noticed that air attached to other particles of coffee frequently caused them to rise to the surface. Here they too lost their volatile oils and contributed little to the strength of the brew. As for particles in the water itself, they soon saturated the fluid to the point where it could no longer absorb oils efficiently. Rumford reasoned that a new method of brewing coffee was possible.
If the liquid were perfectly at rest, the volatile particles disseminated in it could not escape, or at least not with the same facility as when it is agitated. In order that coffee may retain all those aromatic particles which give to that beverage its excellent qualities, nothing more is necessary than to prevent all internal motions of the particles, by preventing its being exposed to any change in temperature, either during the time employed in preparing it or afterwards till it is served up.
The idea was to prevent convection currents, those internal motions of the particles. Rumford foresaw that this could be done by pouring boiling water through the coffee in the powdered form, and then surrounding the pot by a jacket of boiling water or steam. Here is the application of these theories. Rumford published this in 1812. It seems incredible, but as you can see, this looks precisely like any modern drip pot. The drip method was Rumford's way of making good coffee. Here is the pot itself, surrounded by a heated water jacket to maintain constant temperature. The constant temperature would prevent convection currents from disturbing the brew. You fill the water jacket here, but put powdered coffee here and poured in boiling water here. The water moves through the coffee, taking with it a maximum amount of volatile oils from the grounds. Count Rumford believed that the water should always pass through the same thickness of coffee to be able to make several different amounts of coffee, 4, 6, or 8 cups, for example, and still keep the thickness of the coffee layer constant. He designed these pots with a set of coffee strainers, each of a specific size for a required amount of coffee. A strainer for 4 cups, a strainer for 6 cups, and a strainer for 8 cups. These were coffee makers for the general public. As you know, there was a certain evangelical desire in Rumford's part to extend coffee drinking to all classes, perhaps as an alternative to alcohol. For the rich, he proposed very large and very ornate urns to serve guests at the sort of elaborate parties and receptions that he himself detested. For the poor, he described a set of coffee pots made of pottery. Here is one of them. The coffee is made right in the cup. The cup, the strainer, and the tamper. With these coffee makers, though they followed the drip method, the heat insulation of the walls was not really good enough to take the place of the steam jacket protecting the flavor of the coffee made in larger pots. Instead, he suggested that the cup be placed in a saucepan containing boiling water. This model of Rumford's coffee pot is just like a modern version which you can buy today. The cup, the coffee strainer, and the tamper. Finally, he produced designs for a portable coffee maker. I don't think these designs were actually built in Rumford's lifetime. However, you can see here that the design works. One reason Rumford may not have actually made this model is that it violates his theory that convection currents should not be set up in the finished coffee. You see, there is no water jacket to keep the liquid at a constant temperature. There is an alcohol lamp to keep the coffee hot. However, the heat from the lamp would certainly set up convection currents in the pot, and those currents in turn would expose the volatile oils to evaporation. Nevertheless, it is very portable. Well, you've seen some of the practical results of one man's theoretical work, and I hope you understand better the relationship of pure physics to applied physics. Rumford first had to understand the theoretical aspect of heat before he was in a position to project his understanding in the form of his very practical and enduring designs for fireplaces, stoves, and coffee pots. To state the same thing visually, you might say that an understanding of this in his laboratory came an understanding of how to make a fireplace work and work well, how to construct stoves, and how to make a good cup of coffee.
In the work of Rumford, you have just seen a piece of scientific research opening the way for a practical invention. This was not by any means the usual order of things in the 18th century, nor even a good deal later. Indeed, a man who has contributed much to the difficult science of thermodynamics could say about 1850 that at that time the steam engine had done more for science than science had done for the steam engine. By 1900, this and similar scientific wisecracks had given rise to a cliché, that of practice being always ahead of theory, and theory trailing behind, discovering with difficulty how to explain the process devised long before by the practical inventor. For a long time, this cliché was not without foundation, although even in the 18th century, it was contradicted in the work of Rumford. But nowadays, it is becoming less and less applicable. There have also been other cases in which a theory had to wait a very long time until, more or less by chance, some useful application was found for it. A famous example of this is that of the ellipse, studied by Euclid, the Greek geometer, around 300 BC, finding its use in astronomy 2,000 years later at the hands of Kepler. Today, it is less and less true that invention goes before theory, or that theory must wait years or even centuries before being used in practice. Today, there is a close alliance between science and industry. To quote a very recent example, in November 1956, 3 American physicists received jointly the Nobel Prize for their invention of the transistor. All 3 men, Dr. Bardeen, Dr. Brattain, and Dr. Shockley, were working in the Bell Laboratories. There, they greatly advanced our knowledge of the very difficult, highly mathematical subject of the physics of solids. But they also had clearly in mind what practical advantages would follow if certain questions of pure physics were solved. And so it was that they invited this new device, the transistor, this little thing I'm holding now in my hand. This has already caused quite a revolution in radio, and yet it seems to be only at the beginning of its development. And in this same broad field, the physics of solids, other scientists are just now working feverishly at theoretical questions. When these are solved, they will usher in completely new techniques in metallurgy. This new metallurgy, based on pure science, will be completely different from the empirical art which we inherited from the artisans of the Bronze Age. This is a very new phenomenon which we are witnessing. One after another, techniques which 40, 20 years ago were mostly empirical, that is, founded on matter-of-fact remarks, duly noted, to be sure, but not really understood. These techniques, one by one, are becoming highly scientific, because some recent progress of theoretical science has just made possible some useful practical process, or the creation of some new material with unheard of properties. As a result, we now need in every field of industry an unlimited number of well-trained young people, men and women, to solve the problems which lie tantalizingly just beyond the reach of the older generation. It is not possible anymore to count only on a mere handful of young scientists to man the research laboratories of tomorrow. It is the whole nation which needs to realize the challenge of the scientific age in which we are now living. Things are changing terribly fast in the field of physics, in that of chemistry, in biology. For example, of automation, or of silicones, or antibiotics. Everywhere we seem to know how to turn the latest advances of pure science into something practical. This, of course, is just what Count Rumford did. And today, science and industry seem to have taken his example to heart.
This is National Educational Television.